So, Christian, yes.
Sorry, do we have all the tools to do the homework as of right now?
Yes, you do. You have all the tools to do the homework right now. But today we're going to go over the example of what I think is probably the most involved one. And this is an energy balance on a flash separator. So we should all be very familiar with the flash separator. Now for this particular example, we're going to have a mixture of acetone and benzene. An AB mixture. It's going to be 50-50 molar composition being fed at 1 mole per second and at 20 degrees C and 1 atmosphere. So this is all going to be liquid. We're going to operate the flash separator at 1 atmosphere pressure and at 69 degrees Celsius. We have an unknown heat requirement. Vapor stream and a liquid stream. This is it. Our goal is to solve for Q. How much energy do we need to operate this process? What is the temperature of the L and the V streams?
69.
Why?
Because that's the temperature your flash separator's operating.
Right, so in order for the liquid and vapor to be in equilibrium, they have to be at the same temperature and the same pressure. So if we're operating the flash unit at 69, that means both of these two streams have to be at the same temperature and same pressure. Otherwise, they won't be in equilibrium. If they're not in equilibrium, we can't use any of the tools that we've developed so far with Raoult's law. Question?
Will that always apply to flash separators, that the top and bottom stream will always be at the same temperature and pressure?
Yes, for flash separator, we're using one equilibrium stage. And at an equilibrium stage, you have to have the same exact conditions. The same is true for liquid-liquid separator as well. So if you wanted to use a triangle diagram for liquid-liquid separation, you would have to assume that the top and bottom streams are in equilibrium. Right? So that's how you could actually read off the triangle diagram. If it's not in equilibrium, then we can't use any of the thermodynamic tools we have. We have to somehow then estimate what it might be. Okay, so in this particular situation, I have previously calculated that the minimum operating temperature, or the bubble temperature, would be 65.7 degrees Celsius, and the maximum operating temperature, or the dew temperature, was 70.2. So based on this information, do we expect this to be mostly vapor or mostly liquid? I'm getting a little bit of both. Mostly vapor, right? Because we are closer to the dew point than we are to the bubble point. What is our first step? What is our first step in executing this problem? Can we directly solve for Q?
Solve for the flow rates and compositions.
Bingo, that's the first step. As an exercise, let's write out our energy balance, just to see what we're in for. So du dt is equal to what? Just this term here. What is du dt? U is the internal energy of this system right here. Is it changing as a function of time?
No.
No, so this is 0. This is equal to So here is our energy balance. We know some of the molar flow rates, right? We know the inlet conditions, 50-50, but we don't know We know all the inflow rates, but we don't know their enthalpies, we don't know the outlet flow rates, we don't know their enthalpies, and we don't know Q. So it turns out we don't know a whole lot of information about this problem. But the first step was to solve for the flow rates and balance this out as a normal flash calculation. So let's work on that part. So the acetone vapor pressure at the system temperature and for the benzene we have the vapor pressures. Now I'm not going to go through the entire flash calculation, but of course, since we just went over this on the exam, and lastly we have two of these and one of each of these. Now, for the sake of just so that everyone has the information available, I'm going to put down the solution to the material balance just so if anyone wants to go back later and look at it, they can. Okay. Those are the solution to our flash calculation. Now, one thing that I want to highlight here are these two equations. So if we add up all of the liquid mole fractions, that has to equal 1. Right, how we get this equation here is that we take the summation of all of the number of moles of every species I, and we just say that's the total number of moles. Now, if we divide both sides of the equation by the total number of moles in the system, this tells us that the summation of the mole fractions is equal to 1. Right, that's how we derive this equation. So all this equation is here is just saying that we're defining what the mole fraction is. But what it doesn't say, right, is if I add up x of a plus y of a, that does not have to equal 1. So hopefully that's not a mistake that anyone made on the exam. Right? If we add up x of a plus x of b, this equals 1. Y of a plus y of b, this equals 1. But not across the phases. Right? It's not xa plus ya equals 1. It's not xb plus yb equals 1. All right. So now what we can do, we've got our material balance done. We can fill in our process flow diagram to make things a bit easier for us. So on this stream right here, the vapor stream, we need to calculate what the molar flow rate of all of these individual species are. How do I know what the molar flow rate of acetone in the vapor stream is? What should I calculate?
Do a balance.
So I have all the numbers up there. What numbers do I put in here?
You do 0.721 is equal to your...
So this is V, so V is equal to 0.721. So I could write that N of acetone in the vapor is equal to this times by the composition, so 0.554. This would be 0.399, assuming I did all of my math correctly. N dot B vapor, molar flow rate of benzene in the vapor stream, is we take the 0.721, times it by that term up there. Let's see, Y of B is 0.446, so this is 0.322. So this is the total flow rate times by the composition of each of the individual streams. So I could write that out as XBV times V.
Will that be Y for the vapor?
Yes, correct. YBV. And we do the same thing for the liquid stream. Okay. And L, I'll put that in here as well, just so we have it all in one spot. So far, so good, right? This should all be a review of what we just were quizzed on the exam. No questions, good. Now, material balance. So, looking at our energy balance, we have all of our ends figured out. We know the flow rate's in and the flow rate's out. Next step is we need enthalpies. So if we had a big table of all of the possible temperature and pressure conditions from acetone and benzene, we could just look them up. What phase are you in? What's your temperature? What's your pressure? Grab a number, and we're finished. But we don't. Right? So now we have to find a way to calculate our inlet and outlet enthalpy conditions. So the way that I like to do this is I like to actually build the table. Right? Because if we have the table, it's pretty easy to solve. Right, just like any steam table calculation, right? You just grab the numbers out of the book and plug and chug away. So we're going to construct our own. So we have our feed, our liquid side, and our vapor side. All right, so we've built our steam tables for acetone and benzene. What do we know? How do I start to calculate these numbers? What do I need to assume?
Reference state?
Reference state. Let's take some time and talk about what reference state should we choose. First question, does it matter?
No.
No. Mathematically speaking, it doesn't matter. Now, there are some reference states that could make things really difficult and some that could make it a lot easier. Yeah.
The inlet flow conditions?
Inlet flow conditions, that's one. Let's talk about the pros and cons of using the inlet flow conditions. So if we choose the inlet flow conditions, right, we set this equal to 0. Which is nice, because then we could just fill in our table here. 0 and 0. How do we calculate the enthalpy of the liquid stream then? It's possible. You can use this as a reference state. This is not a trick question. How do we calculate the enthalpy so I can put a number in this table here for the liquid stream? Right, we've chosen a reference state. Now we have to go through steps where we know how to calculate the enthalpy, either by pressure changes, temperature changes, or phase changes. Yes?
It looks like it's just a temperature change.
Exactly.
It's the same pressure.
So this one's trivial. It's just the integral from T in to TL, C sub P, dt. Right, we are going from our reference state condition, or I could say T ref if we wanted to be a bit more general. And the same thing would be done here. So the only difference between the enthalpy of the liquid for acetone and the enthalpy of the liquid for benzene is that they have different heat capacities because we've started off at the same reference state. What about for the vapor stream?
You have a phase change and a temperature change.
We have a phase change and a temperature change. So how do we get to that point?
You could do
The same integral plus P delta V. Or
Well, so the P delta V is not going to be the big factor. It's going to be the phase change. We're going to neglect any pressure changes. And also because this is a constant pressure system.
Is it just a sign change for the?
Well, so for the vapor one, there's a couple of tricky issues here, right? In a flash separator, we are never going to be using the normal boiling point of any of the fluids that are in the back of the book for the heat of vaporization. Because if we look at a TXY diagram, I'll call this Z of acetone here, and this is the TXY diagram. Now, acetone is the more volatile species, so it has the lower boiling point, and this one's up here. This is an ideal system. It'll look like this. We're at a 50-50 mixture near the dew point, so we are at about a condition like this or so. Now, what is this point right here?
Boiling point of
This-
acetone.
Bingo, this is the boiling point of acetone. Up here is the boiling point of benzene. We are right in the middle. Right, so vapor-liquid equilibrium is a bit tricky because you have one fluid that wants to be a vapor but is forced to be a liquid. You have another fluid that wants to be a liquid but is forced to be a vapor. So you have to calculate the heat of vaporization at conditions that are far away from the normal boiling point for either of the two fluids. So you always have to go through this process now of dealing with the vapor enthalpy, choosing a path that goes through known conditions. So what we could choose to do is we're starting off at 20 degrees C. So we could choose a path of heating the fluid up to its normal boiling point, boiling it, and then changing the temperature to get down to the outlet conditions there. That's one path that we could choose. And in fact, if you choose the reference state as 20 degrees C in liquid, that's the path you would likely have to choose. Okay? We could also choose a completely arbitrary reference point. Let's say 0 degrees C in 1 atmosphere. In which case we would have numbers for the feed, we would have numbers for the liquid, and we would have numbers for the vapor. Now I personally prefer a slightly different approach to to choosing a reference state. I like to use the liquid as the reference state. Now the reason why, and I'll go through the example using the liquid as the reference state. What do we have to do to go from the liquid to the feed?
temperature change.
It's only a temperature change. What do we have to do going from the liquid to the vapor?
Phase change.
It's only a phase change. Right, so it just simplifies the number of steps. But ultimately, choosing the feed as the reference state, it's kind of a similar amount of work, right? Because the hard part of this one here is calculating the heat of vaporization at the system conditions. So in this case, for the feed, it would just be, we would integrate from our T reference to our inlet conditions, like so. Is this going to be a positive number or a negative number? Why is it going to be negative? Right, your reference temperature is actually at a higher value than your inlet conditions. So here I could write out T ref is equal to, and vapor. So we would expect this to be a negative number. And for here, this is just the heat of vaporization at the reference temperature. So now, strictly speaking, right, this should all be plug and chug. If we remember the steps to calculate these different processes. So in thermodynamics, what we like to describe things as we're changing its state, right? You're changing the pressure and temperature. So a collection of variables, pressure, temperature, phase, we wrap that up and we call it a state. So we're changing the state, in this case, from the reference state to the inlet conditions, or from the reference state to the vapor conditions. And how we do that is we just imagine that we're sort of lassoing or putting a balloon around an element of this fluid. We're transforming it through any arbitrary path that we've selected that allows us to get from one point to another. But that's called a state change. So from here, the liquid one to the feed is pretty straightforward. The vapor one is where we're going to be spending a bit more of our time. We did talk about it last week, but we also had an exam, so it might have slipped away, unfortunately. So let's talk a bit about calculating the enthalpy feed. So in this case here, what we're doing is we are calculating a delta H from T ref to T in. Now this notation here, delta H, this is the final state minus the initial state. What am I assuming is my reference enthalpy?
0.
0. I don't have to, though. I could have said it's 100. I could have said it's 1,000,000. But to make our lives easier, it makes the most sense to say 0. Now, this is the key critical step in how we can take our equations that we know for delta H, in this case, the integral of C sub p dt, going from 69 to 20 degrees Celsius. And I can write a little I here so we can denote what species we're talking about. Either it's acetone or benzene. We only know how to calculate changes in enthalpy. Changes with phases, changes with temperatures, changes with pressures. But in our table, we need an absolute number that we can plug in. So how we get out an absolute number is by assuming our reference state is equal to 0. So this right here is the key step that unlocks all of our energy balances. We know delta H is equal to the integral of C sub p dt. This is nothing more than the definition of heat capacity. C sub p is defined as how the enthalpy changes with how the temperature changes. So in this equation, all we're doing is moving the temperature to the side and integrating the expression. So this is nothing more than the definition of the heat capacity. So all we're doing is unpacking what someone else has already put together in a book in a table of heat capacities. So all we're doing is unpacking previous experimental data. Now how we get the actual number is then we know that delta H is equal to final minus initial. We set the initial condition to 0, and then we move on. Yes?
Sorry, and you said the initial, just to clarify, the initial is 0 because...
Makes it easier. We get to choose the reference state.
Okay.
So we choose a reference state that is convenient, and we set it equal to 0. But we could have said the reference state in the liquid is equal to 100 joules per mole. And we could have done that. But we just said, let's just set it equal to 0 to make it easy for ourselves. Because otherwise we'd just be adding and subtracting 100 to all these different expressions and it all cancel each other out. This process makes sense. Okay. So the numbers that we would get out if we were to crunch it, we would get minus, let's see, 8.9, and these are all in kilojoules per mole. And this one is minus 9.3. No different than what we've done so far. But the key thing is don't forget how we got here. Understanding reference states and how we're calculating state changes, that is the core difficulty of all of energy balances that we're going to be working on. This step right here, I'm confident that everyone can do this step. Right? It's something that you've seen many times over again potentially and did in your Thermo 1 class, but focusing on the reference states here, this is really the key part. Now let's talk about heat of vaporization. Now last week we talked about a diagram, an HT diagram. Here we have the enthalpy of a fluid as a function of its temperature, and I have drawn two lines for the two different phases. We have the enthalpy of the liquid at some subcritical point where it's a liquid, and we have the enthalpy of the vapor at the same temperature. As we increase the temperature, we get closer and closer to the critical point. Eventually, these two lines will cross at the critical point. The height the change between the liquid line and the vapor line, that is your heat of vaporization at some temperature. Yes?
So on this graph, there's the enthalpy of the vapor and the liquid at the same temperature. Wouldn't that mean that the top line would have to be at less pressure?
Yeah.
Okay. All right.
It's a fair statement. So what you could also imagine then too, if this was a confusing engineering chart, a bunch of curved lines at different pressures as well. So you could definitely have that. Mm-hmm. Okay, so now the key feature here though, right, is that we have the heat capacity of the vapor and the heat capacity of the liquid have different slopes, right? The slope is defined as the heat capacity. Now right now I've drawn this with constant heat capacities, but in reality there'll be curved lines, and generally they should look kind of arched like that. But the same concept holds true. It's just a simpler drawing to keep them nice and straight lines. So the reason why the heat of vaporization gets smaller as you increase the temperature is because the differences in properties between the liquid and vapor become more and more similar. Additionally, it takes more energy to heat up a liquid than it does to heat up a gas, because liquids have neighbors that they have to get along with and push around. So when you're heating up a liquid, you have to kind of deal with your nearest neighbor molecules. When you're heating up a vapor, especially if it's an ideal gas, you have no nearest neighbors, right? There's less energy that it takes to just increase your temperature. So, the question is, how do we want to calculate the heat of vaporization at a temperature where we don't have it tabulated? Normally, we're only going to have this tabulated at the normal boiling point. But in this case here, we have to choose one that's at a lower temperature for benzene and at a higher temperature for acetone. So the boiling point for benzene is 80.1 degrees C, and for acetone is 30. Oops, that's not right. It is 56 degrees C. The heat of vaporization at the boiling point for benzene is 30.8.
That's supposed to be.
Bottom right
Yes. Don't know why I'm so bad right now. There we go. Thank you. So
those are all at standard temperature and pressure?
at 1 atmosphere, right? The normal boiling point here is at 1 atmosphere pressure. Now we could be operating this flash separator at a totally different temperature and pressure as well, right? We could elevate the pressure significantly higher to get this thing closer to its critical point, and it would change our calculations quite a bit. Since we're at 1 atmosphere, we're relatively close to the normal boiling points, and so this process that we're going to show right now is not going to be so totally off from if you just neglected it and assumed these were constant. But I want the pathway to be more apparent, because if this was at a significantly higher pressure, you would be having to estimate the heat of vaporization at, let's say, 200 C, right? Which is a lot different than going from 80 to 69 or 56 to 69. So in the case of benzene, right, we're boiling it at a lower temperature than what it normally wants to boil at. So is this number going to be higher or lower in our energy balance?
Lower.
Higher?
All those in favor of lower. All those in favor of higher. It's going to be higher because we're pulling it further away from its critical point. Right? The heat of vaporization only increases as you lower the temperature. In the case of acetone, right, its normal boiling point, let's say, is right here. We're estimating it at a higher temperature, which means the difference between liquid and vapor gets smaller. So it's another way to do a double check consistency. So the procedure. Number one is we first have to heat or cool the liquid to its boiling point. Step 2, vaporize. And step 3, heat and cool to whatever the outlet conditions are. So in the case of benzene, we're going to have to heat it up from the outlet conditions of 69 to 80. We vaporize it following the tabulated information that we have access to, and then we cool it back down to 69, which is the outlet temperature of the vapor. Yes?
Just to clarify, those delta H's are at the normal
Yes.
boiling point. Okay.
They would be at T boil.
Okay.
Now, alternatively, we could use correlations that are average fits to what a typical fluid might behave as. So in the case, there's one that a lot of students really like because it's pretty straightforward to use. We call it, I'm going to write it on the board, called the Watson's correlation. So alternatively, we could use correlations. So this is the Watson correlation. Now what we're doing here is we have the heat of vaporization at some T1. In this case, this is probably going to be the normal boiling point where it's tabulated. Then based on how far away it is from the critical point, we can estimate what we would expect the heat of vaporization to be at some T2. So how we would apply this correlation for this particular problem, I can scoot it down, hopefully we can see everything here. But for benzene, at 80 degrees C, this is our T1. Our heat of vaporization at T1 is 30.8 kilojoules per mole. That would go here. We would have to look up what its critical point is. And our T2 would be 69. Now, of course, we want to convert all of this to Kelvin as well. Wait, actually, no, it doesn't. Wait, does it matter? No, it doesn't matter because it's a difference between these two. So you could keep it in Celsius if you wanted. Yeah.
Is that exponent?
Yes, exponent to the 0.38 power.
Yeah, so where does that come from? Is that just from experiment?
Best fit.
experiments?
Yeah. So all they're trying to do is generalize this curve here and calculate based on how far away you are from the critical point, how this is going to work out. So the Watson's correlation, I'm okay if you guys use it. But it is critical that you understand this procedure because there may be instances where we cannot use the Watson's correlation and we have to understand the 3 individual steps that we're going to take. All right, so let's go through this example here. I'm going to erase the and we can finish up the calculation. So for benzene, I am calculating the delta H going from my reference condition to the conditions of the vapor stream. Now I can write this overall process as some enthalpy of the vapor, and this could be for A and B, minus the enthalpy of my reference state, which I have very conveniently said is 0 to make things easier. So now I just need to calculate the individual steps going from my reference state to my vapor state. And I have 3 individual steps. The first step, to heat the liquid, plus to vaporize it, to cool the vapor. And this is for benzene. For acetone, it's different. So if I write this out, first I'm going to be heating the liquid. So I'm going to go from my reference temperature to the normal boiling point using the heat capacity of liquid benzene. And we're not assuming it's constant. If you did assume it was constant, you would have to decide, is it a constant of 69, is it a constant of 80, is it a constant in the middle, whatever the conditions are.
If you did assume it was constant, you could just do CP times delta T.
Correct.
Couldn't you?
Yep. But the reason why oftentimes, if you build a good spreadsheet to do these calculations, just crunching the numbers to get a C sub P, if you're looking up out of the back of the book, is often a difficult enough task that integrating it isn't much more difficult. Right, because really what I have when I do write homework examples and problems, I have a spreadsheet where I just type in the A, B, C values and D values, and then it automatically calculates the delta H's. But if you just wanted to calculate the C sub P that was constant, it's really almost the same amount of work. Right? If you've already built the tool, it's almost just as easy to not assume constant heat capacities as it is to assume constant heat capacities. All right, next step. We vaporize benzene at T equals 80.1 degrees C, and just so happens that we have tabulated values for what the enthalpy of vaporization is at that condition, 30.8 kilojoules per mole. And then the last step is we have to cool it back down to the outlet conditions, 80.1 to 69, but in this case, it's the C sub P of vapor benzene, dt. I think I have it written here somewhere. So the numbers here, 1.6 kilojoules per mole plus 30.8 kilojoules per mole, and then minus 1.1 kilojoules per mole. So the difference in the heat capacity between the liquid and the vapor tells us why the heat of vaporization changes as a function of temperature. In this case, it's not that big of a deal, right? 0.5 kilojoules per mole. Question?
The C sub P vapor versus liquid is, I haven't really looked in the textbook yet,
Mhm.
but are there separate values
Yes.
given for the phase?
Yeah, they'll have to be.
Yeah.
And oftentimes the book will have much more limited data of the heat of vapor, sorry, the heat capacity of the liquid than does the vapor, because it's a lot more vapor stuff goes on. Yeah.
Sorry, what is, so you have delta H of vaporization plus delta H, I just can't do that. Here's such good.
This here?
No, up top.
Liquid.
Cool.
Yeah.
So heat, liquid, cool, vapor.
Okay, thank you.
And so the number here we get is, actually, right here. Where did I have it? 31.3 kilojoules per mole. And we can add it to our chart. This is for benzene, 31.3. Now for acetone, it's the same general procedure, but things are flipped around a little bit. So in the case of acetone, it's the same general procedure, but we're flipping when we're heating and when we're cooling. So first, we have to go from our reference state, 69 degrees Celsius, to the normal boiling point, which I have since covered up. It is 56. So we're cooling down the liquid now. Then we are going to vaporize it. Then we are going to heat the vapor back up to the system conditions. So exactly the same procedure, except the normal boiling point has changed. But if we look at it, right, the math takes care of everything. The formula is exactly the same. Reference state, boiling point. Boiling point, boiling point, boiling point, reference state. But the sign will be switching. But we don't have to worry about it, right? Because the integral takes care of all things. You don't have to be clever, you don't have to switch things around, keep it exactly the same, because when we flip the bounds, all we're basically doing is changing the sign. So in this circumstance here, this will be negative and this will be positive. So here at minus 1.8 kilojoules per mole plus the heat of vaporization, 30.2. And lastly, the vapor side is plus 1.1 kilojoules per mole, and that gives us a total amount of 29.5. I can't even read my own handwriting. Yeah, 29.5. And we fill it into our chart. And we are almost there. Now it is strictly a plug and chug problem. We have enthalpy values for every single one of our components, for every single one of our streams. We have molar flow rates for every single one of our components and every single one of our streams. And so we can apply our energy balance. So coming into our system, we have the enthalpy that acetone carries with it as a liquid at 20 degrees, the enthalpy that benzene carries with it at 20 degrees as a liquid. Leaving the system, we have, well, nothing coming out of the bottom, because we assume that's 0. And then coming out of the top, we have the enthalpy of vapor acetone and the enthalpy of vapor benzene. So in our equation, if we assumed an arbitrary reference point would have 1, 2, 3, 4, 5, 6 entries plus the Q, by assuming a 0 reference state for one of our streams, we only have 4 entries plus the Q. But being neat and organized really helps in your calculations. So what I would really recommend doing if you were to solve this problem is to not do it by hand by any means possible, right? Do it on an Excel spreadsheet. So what I would recommend is when you build your big table where you're filling in your enthalpy values, add an extra column for the flow rates of each of the individual species, right? Because then you can do N of the feed times by its enthalpy, N of the feed times by its enthalpy added together, N of the feed times the liquid, or sorry, N of the liquid times the enthalpy of the liquid, and so on, added together, right? So think about how to organize these calculations to make it easier. But if they're all willy-nilly all over the place, it's going to be really difficult to troubleshoot and also to find what you need to calculate. But if you build this table to include your flow rates, then hopefully you can envision a way that you can just have an automated system of dragging the same equation over in Excel or in MATLAB, whatever the case you want to do is. The final value for Q, when we go through all of the number crunching, is 30.9 kilojoules per second, which is a lot of energy. Right? Vaporization is an endothermic process. It requires a lot of energy input. And in a flash separator, if we're starting off with a liquid feed and we're creating a vapor, we're definitely going to have to be putting a lot of energy into the system. Right? And this is just for 1 mole per second. So any real process, this vaporization is going to be taking megawatts of energy very, very easily. Right? So chemical energy is a huge amount of energy drain. So vaporization processes and vaporization separation mechanisms take up a massive quantity of the overall energy consumption of this country. Right? I think distillation, I've heard, consumes like 10% of the world's energy or something like that. It's a crazy high number. Right? So if you can design a better separation process with, let's say, a membrane or a liquid-liquid separation, you'll actually end up saving a lot of energy. And that's why ethanol is not really the best alternative biofuel, because in order to get the ethanol, you have to distill it from water, which takes a lot of energy. Where do they get that energy from? Well, typically burning fossil fuels. So it's kind of a cyclic process that doesn't make a lot of sense. All right, check out the homework and see everyone on Wednesday.